Hi, everyone. My name is Ben. I'm a third-year PhD student at UCLA, and I'm advised by Professor Miriam Kim, and this is a collaboration with my lab mates at SEAL at UCLA. So to begin, I wanted to first talk about or give some context for how our work fits into the larger ecosystem for machine learning and hardware accelerators. Today, engineers rely on high-level frameworks like TensorFlow, ONNX, and PyTorch to build and train models, but we also expect to be able to execute these models on a wide range of hardware ranging from CPUs, GPUs, FPGAs, and more. What enables these models to run on this such wide variety of hardware are machine learning compilers, and a key technology that powers many of these compilers, like OpenXLA, is MLIR. And so ensuring the correctness of these compilers is critical for modern machine learning workflows. To give some more background, MLIR is a compiler framework, part of the LLVM project, but it differs from traditional compilers in that it's designed to be extensible. So instead of a single intermediate representation, MLIR encourages developers to define domain-specific IRs in the form of dialects. This modularity and flexibility has led to rapid adoption. Over 30 projects have adopted MLIR since its public release in 2020. But this flexibility also creates a challenge for test generation. In this table, we highlight 4 MLIR projects, which alone define over 100 compilation passes, 74 different dialects, and over 1,000 operations. And so because MLIR is an intermediate representation, and it's not public-facing like C, so it's not fixed to any particular standard, dialects are free to be added or updated frequently. And so any effective testing strategy needs to be able to scale to keep pace with this rate of development. So that brings us to the key question that we try to answer in this work, which is how can we bootstrap dialect-specific custom generators without the significant manual effort required? There are two main challenges with existing approaches. The first is that custom generators, and in particular grammar-based fuzzers, require detailed dialect-specific grammars in order to generate valid inputs for MLIR. While MLIR dialects do share a common syntax, generating inputs that only conform with the base MLIR specification wouldn't yield well-formed dialect-specific operations. And so a further problem is that these grammars require continuous maintenance. So even if you have a dialect-specific grammar, you need to continually update it as these dialects change over time. And so manually creating and maintaining these accurate grammars doesn't scale for the needs of MLIR. The second challenge is that context-sensitive constraints need to be preserved. We need to generate inputs that satisfy not just what a context-free grammar can constrain, but the rules of a context-sensitive, rules that are context-sensitive. In MLIR, there are general constraints like the fact that some rules or some values can't be redefined in the same scope. And there are also dialect-specific constraints like some attributes that must match definitions defined elsewhere in the input. So with these two key challenges, given the diversity of these MLIR dialects, how can we bootstrap these effective dialect-specific generators? In our work, we propose the following solution, which is to synthesize custom mutations that preserve these dialect-specific grammars or dialect-specific constraints automatically. And that brings us to the key insight behind SynthFuzz, which is that we can use seed test cases to automatically synthesize custom mutations that implicitly encode these constraints. We draw inspiration from prior work on automatically learning program transformations and edits from examples, and learn two key features to make our mutations valid. The first is positioning. This is where we determine where the mutation should be applied in the recipient test cases. And the second is substitution. When we apply the mutation or insert the content, it needs to be consistent with its new context. And so SynthFuzz's mutations are parameterized. That means that when a mutation is applied, these placeholders are automatically substituted with new values that are appropriate for the new context. And so by automatically synthesizing these custom mutations, we obviate the need for the manual effort required to write these dialect-specific grammars or constraints. So to give an overview of how SynthFuzz works, SynthFuzz works in 3 main stages. I'll go into the details later, but first, SynthFuzz starts with seed test cases that we parse with a base MLIR grammar. And crucially, this grammar isn't dialect-specific, and so we can apply it to any MLIR compiler. And then in the first step, what we do is we synthesize mutations from the parse trees that we generate from the base MLIR grammar. And then in the second step, we locate where we can apply these parameterized mutations by comparing them with the recipient parse trees. And then finally, we instantiate these mutations by substituting the appropriate content and to finally create our mutated parse trees. So starting with the first step of SynthFuzz, we begin with a seed MLIR test case, and then we parse it with the base MLIR grammar. Then we select a random subtree within this parse tree in order to be the code fragment that we want to insert into a new context. The subtree that we select, we call the mutation, and the rest of the parse tree becomes the context that we'll use in order to locate and also to parameterize the mutation. To make this mutation adaptable to new contexts, we parameterize it using a heuristic. Strings or parse tree nodes that appear both within the selected mutation subtree and the surrounding context are replaced with placeholders that are concretized in a later step. The intuition is that nodes that appear both in the mutation and the context represent parts of the IR that are context dependent, like variable names or types that need to be substituted when we instantiate the mutation. Now that we have a parameterized mutation, we need to find a suitable location that we can insert this for particulars for recipient test case. And we do so by inserting the parameterized mutation by matching the context in terms of which parents it has, or by matching its prefix or suffix. So by positioning the mutation in this way, we ensure that SynthFuzz has necessary context to concretize the parameters. In the final step, now that we have a suitable location and a parameterized mutation, we can finally concretize the mutation. We do this by traversing the parse tree of the target recipient test case relative to the insertion location and find the nodes that are in the same relative position as in the context of the parameterized mutation. So in this example, the parameters B and C are bound to the concrete values %0 and I4, since they are in the same relative position within the parse tree and the parameterized mutation. And these concrete values are then substituted into the parameterized mutation to result in a mutation that's consistent with its new context. To evaluate SynthFuzz, we answer the following research questions. First is we look at how effective SynthFuzz is in terms of increasing code coverage. Secondly, we look at the input space coverage of SynthFuzz. And finally, we do an ablation study in RQs 3 and 4 to see the effect of parameterization and context-based positioning. To go more into detail about input space coverage, we measure the semantic coverage of the generated IR by counting the number of unique pairs of operations that are related by control and data dependencies. The idea here is that simply generating long but isolated chunks of code isn't sufficient to effectively test the compiler. We want our mutated IR to consist of operations that are meaningfully connected via control and data dependencies, forming realistic program fragments. And this is particularly important because compilation passes in MLIR frequently work by matching and transforming patterns of operations that are connected in this way. Now looking at cumulative branch coverage, we find that SynthFuzz achieves the greatest improvement for compilers that use more dialects. So for example, MLIR, which includes a dialects in the core MLIR project, SynthFuzz achieves a 1.5 times greater branch coverage. And in CircuitOpt, which is a compiler for hardware design and defines 26 unique dialects, we see an about 1.2 times improvement in branch coverage. Next, we look at input space coverage, and we see that SynthFuzz outperforms all baselines in terms of both control and data dependencies. And this demonstrates how SynthFuzz can generalize to new dialects without the need for manual effort to hand code custom generators. Then looking at a closer look at Onyx MLIR, which is a compiler particularly for ML models, we find that SynthFuzz can match the performance of domain-specific fuzzers like Nuri that generates ML models at the input level. And what this shows is that fuzzing at the IR level has particular advantages compared to fuzzing at the model level or input model level. In RQs3, we look at we do an ablation study to look at the effect of how we anchor the mutation based on its ancestors or left or right prefix and postfix. And so we find that generally increasing the amount of context that we consider when positioning the mutation generally increases the amount of the proportion of valid test cases that we generate. But this comes at a trade-off because it can also reduce the input space and branch coverage. So in a sense, increasing the requirements for positioning the mutation generally lowers the diversity of the test cases in exchange for higher validity. And finally, we look at the impact of parameterizing mutations. In this table, we show a breakdown of where errors are emitted from in the MLIR compilers. With parameterization enabled, we see that SynthFuzz or the distribution of where the errors are emitted from changes from general MLIR to dialect specific. And what this shows is that parameterizing mutations enables SynthFuzz to better exercise dialect-specific code, since these inputs are now satisfy these general MLIR constraints. And so in conclusion, we find that testing MLIR compilers are challenging because of the rapidly evolving dialects. And so to obviate the need to write dialect-specific grammars and constraints, we synthesize custom mutations from existing test cases. And we find that fuzzing MLIR compilers with synthesized custom mutations generally increases code and input space coverage. And though our work here focuses on MLIR, custom mutation synthesis is a generic approach, and so it can be applied to other domains to reduce the effort of writing custom test generators. For example, JSON schemas like CloudFormation and SQL dialects. And thank you.